Okay, so yesterday we discussed bosonic strings, okay, and that was more a warm up exercise, but so today we will do heterotic and type 2. In fact, I will focus mostly on heterotic because the generalization of type 2 is straightforward. Okay, so instead of trying to discuss both, I will just focus on one of these. Okay. And we will see that even though the bosonic string was a warm up, okay, we will be able to use many of the results that we had already obtained in bosonic strings, okay, just by putting in a few more details when we go to heterotic or type 2. So, let me begin by reviewing the worldsheet theory. Okay. Again, as I said, I will focus on heterotic string theory. If you want to go to type 2 string theory, you essentially have to do whatever I am doing on the right sector, you have to do it also on the left sector of the worldsheet. Okay. So, the heterotic worldsheet theory contains a matter superconformal field theory with central charge, which is 26 on the left moving side and 15 on the right moving side. And the ghost system of the heterotic string theory contains the usual left moving ghosts B bar and C bar, which carries a total central charge of minus 26 and cancels this 26 over here. Okay. In the right moving sector, it has the BC ghosts, which carry central charge of minus 26. Okay. But besides the BC ghost, it also carries beta gamma ghosts, which are associated with the worldsheet supersymmetry. And these have total central charge of 11. Okay. So, together the ghost system has total central charge of minus 15 on the right hand side, and that cancels this plus 15 from the matter superconformal field theory. Okay. So, the total central charge is 0 both on the left and the right sector. Now, for doing string perturbation theory, okay, one convenient formalism, okay, that one employs is to bosonize the beta gamma system. Okay. Now, beta and gamma are of course already bosonic ghosts because they are associated with supersymmetry. Okay. But what one means by bosonization is that you express this in terms of bosons, okay, scalars, which I have denoted by phi, okay, which are in fact spin 0 objects. Okay. But because e to the phi is fermionic, okay, we have to multiply this by another fermionic field eta. Similarly, e to the minus phi is also fermionic, so you have to multiply by another fermionic field del xi. Okay. So, we trade in gamma and beta in favor of these 4 fields eta, xi, and the 3 fields eta, xi, which are fermionic, and the field phi, which is scalar. Okay. So, I should also add that xi, even though it is fermionic, it has the wrong spin, it is spin 0 fermion on the worldsheet, and this is spin 1 on the worldsheet. Okay. So, once we have bosonized the ghost system in this way, okay, we generate a new quantum number which is called a picture number. Okay. So, we have altogether 3 quantum numbers which are of relevance. The ghost number we are already familiar with from the bosonic string theory, picture number which arises after this bosonization, and the GSO quantum number, which is this is a multiplicative quantum number, okay, which is a given field rather odd or even under GSO. Okay. So, here are the ghost number assignments of the CB gamma beta system. Okay. So, C contains ghost number 1, B contains ghost number minus 1, gamma ghost number 1 because it is the super partner of C, and beta ghost number minus 1. Okay. And all of these fields, original fields, carry picture number 0. Okay. So, the picture number in fact does not exist before you do this bosonization. But after you do bosonization, okay, the xi and eta can be assigned a picture number 1 and minus 1, and that is cancelled by the picture number of e to the phi. So, e to the q phi carries picture number of q. Okay. And one can show that these are conserved charges, okay, up to anomalies, just like the ghost number is a conserved charge up to anomalies. Now, in terms of these fields, one constructs something which is called a picture changing operator, okay, whose role will become clear soon, but this has some specific properties. First of all, it carries picture number 1, Okay. And this is a BRST invariant dimension 0 primary field. Okay. And here is the definition of the picture number. It is simply the anti-commutator of the BRST charge with this field xi that I introduced here. Okay. And when one explicitly calculates this anti-commutator, one finds an answer like this. Okay. So, here mostly it is ghost fields, but we have some matter component TF. TF is basically the superpartner of the matter stress tensor. Okay. And the point I want to emphasize again is the picture number that this operator carries. Okay. It carries picture number 1 because this xi here carries picture number 1. Okay. E to the phi according to this counting carries picture number 1, and if you calculate the picture numbers of these, again you can check that it has picture number 1. Okay. So, it has picture number 1 and also and ghost number 0, okay, because xi has ghost number -1, QB BRST charge has ghost number 1. So, its net ghost number is 0. Okay. So, this operator will play an important role in what we are going to describe later. Okay. So, are there any questions on this? Okay. So, this is basically what we will need to know about the worldsheet theory of supersymmetric string theory. So, let us recall that we had introduced H as the Hilbert space of states which are annihilated by these two particular generators B0 minus B0 bar and L0 minus L0 bar. Okay. So, let me remind you again that L0 is the 0 component, the 0 mode of the Virasoro generators, okay, and B0 is the 0 mode of the B ghost. Okay. Now, we keep these conditions in superstring theory. But besides this, we impose two further conditions that off shell NS sector states are defined to be states in H which carry picture number -1, and off shell Raman sector states are states in H which carry picture number -12. Okay. I should have perhaps added that NS sector states always carry integer picture numbers and Raman sector states carry half integer picture number. Now, I said that a picture number like ghost number is a conserved charge, okay, but it has anomalies, which basically means that if you want to get a non-zero amplitude on a genus G Riemann surface, then the picture number has to be violated by a very specific amount. Just as a ghost number, total ghost number of all the operators on a genus G surface has to add up to 6G minus 6 to get a non-zero answer. Okay. Similarly, what one can show is that the total picture number of all the operators must add up to 2G minus 2 to get a non-zero correlation function. Now, this immediately tells us that for a generic amplitude, if you want to get a non-zero result, we need insertion of picture changing operators. Okay. So, as an example, let us consider an amplitude with n NS sector states, okay, a genus G amplitude with n NS sector states. Okay. Now, n NS sector states will carry a total picture number of -n, okay, but to get a non-zero correlation function we need total picture number of 2G minus 2. Okay. So, we have to somehow go from total picture number -n carried by the operator, so total picture number 2G minus 2, okay, and the way it is done is to insert 2G minus 2 plus n factors of picture changing operators at different points on the Riemann surface. Okay. So, this is the procedure to get a non-zero correlation function in superstring theory. Okay. Are there any questions? Yes.
Do you restrict H is defined projected by the GSO projection, or?
Yeah. So, we include states in H which are GSO even. Yes.
Okay. So
yeah.
You eliminate all the GSO
That's
odd
right. Yeah.
state. Okay.
Yeah, because if you use GSO odd states, then the result will vanish, right? If you take all GSO even except for one, right, the result automatically vanishes.
For type 2 case, we many choice to do the GSO projection.
For
so,
what case?
For the type 2 case, we can choose a type 2A or type 2B
That's
or
right,
the
yes.
type 0 as.
Exactly. So, you assign the GSO quantum number slightly differently for the vacuum.
Okay, yeah.
Yes.
Thank you.
Okay, are there any other questions? Okay. So, given this description of the worldsheet theory, our task now is the same as bosonic string theory. So, let me remind you what are the things you have to do. Okay. The first, you have to find the parameterization of the space Pgmn. Now, I have used two integers m and n for as a level of P, okay, and that simply to distinguish the ns punctures where we insert ns sector vortex operators, and the Raman punctures, okay, where we insert Raman sector vortex operators. So, we will consider typically an amplitude, okay, with m ns sector states and n Raman sector states, and we will denote the corresponding fiber bundle by Pgmn. Okay, and we will see that the information about separate information about m and n are relevant for constructing this Pgmn. Okay. The second task is that for given external states, which we collectively denoted by phi, we need to construct a P form, in fact, the series of P forms omega P on this fiber bundle Pgmn with the desired properties. Okay, and one of the important properties that we need is this. And the final task will be to construct gluing compatible sections and 1pi subspaces of Pgmn. Okay, in fact, these are not independent problems. So, once you have chosen gluing compatible sections, that automatically comes with a prescription for 1pi subspaces. Okay, so really the question is to construct gluing compatible sections. Okay, are there questions?
Yes. Actually, you are talking about a superspace because PMN.
No, we are not using superspace language at all. Right? We are assuming that all the the Grassmann variables have been integrated out. Okay, we will be working in bosonic moduli space, but with picture changing operators. Okay, so there is another formulation of this, okay, based on the supermoduli space. Okay, but we are not using that. So, we are assuming that the supermoduli have been integrated out, and that is the reason why you get the picture changing operators in the first place. Okay, so let me begin by specifying the parameterization of Pgmn. Okay. So, first of all, this involves parameterizing the moduli space of m plus n punctured Riemann surface, because after all you have m plus n punctures, m ns punctures and n Raman punctures, okay. And you also have to choose local coordinates at the punctures. Okay. So, this or well, we do not have to choose local coordinates on the punctures. The choice of the possible choices of local coordinates at the punctures parameterize the space Pgmn. Okay. Choosing a specific local coordinates means you have chosen a section. Okay. So, that is not what we are talking about here. So, this part is exactly the same as in the case of bosonic string theory, okay, because after all you are parameterizing the same space, okay, moduli space of 6g minus 6 of 6g minus 6 dimensional with m plus n punctures. Okay, but now we have additional data, okay, which is the locations of the picture changing operators. Okay. So, a point in Pgmn is specified not only by specifying the local coordinates, okay, but also where you have located the picture changing operators. Okay. So, if you keep the local coordinates fixed, the moduli fixed, but change the picture changing operators, that we consider as a different point on the fiber. Okay. So, the fiber now has gotten extra coordinates. How many extra coordinates? They are precisely 2g minus 2 plus m plus n by 2 complex coordinates that you need to label the locations of the picture changing operators. Okay. So, why this number? Okay. Because if we have m ns punctures, that contributes a picture number of minus m, n Raman punctures gives a picture number of minus n by 2, because Raman states carry picture number minus half. Okay. But we need enough number of picture changing operators to make the total picture number 2g minus 2. So, you need these many picture changing operators to get a non-zero answer. Okay. So, these many picture changing operators you have to locate on the Riemann surface, and their coordinates are additional coordinates on the fiber of PGMN. Is this point clear? So, this parameterizes PGMN. Okay, now we go up to construction of the P forms, omega P of phi. Okay. Now, as in the case of bosonic string theory, the way we will specify omega P of phi, okay, is by specifying how it is contracted with an arbitrary set of tangent vectors. Okay. If we can tell, so contraction of omega P is a P form. If we tell us, if somebody gives the result of contraction of omega P with arbitrary set of P tangent vectors, then you have specified omega P, okay, and that is the way you will specify omega P. So, for this you have to explore what are the possible tangent vectors. Okay. First of all, there are tangent vectors which are associated with deformations of the moduli of the punctured Riemann surface or local coordinates at the punctures. Okay. These are exactly the same as in the case of bosonic string theory. Okay. You label these tangent vectors by simply vector fields on those circles, okay, which tells you how the overlap function changes infinitesimally. Okay. So, these are parameterized exactly in the same way as in bosonic string theory. We do not have to do anything new to do this, to parameterize this. Okay. But now there will be additional tangent vectors, okay, which are associated with deformations of the picture changing operator locations, okay, because picture changing operator locations label the tangent space. So, those will denote by del del yj, okay, and the number of such yj's is 2g minus 2 plus m plus n by 2. Okay. And you have to specify omega p, you have to specify how it is contracted with an arbitrary set of vectors of the first kind and an arbitrary set of vectors of the second kind. Is this okay? Now, let us describe the contraction of omega p of phi with tangent vectors of the first kind. This in fact has exactly the same expression as in bosonic string theory, except for insertions of picture changing operators. Okay. So, let us imagine that you have omega p of phi and you want to contract this with p tangent vectors of the first kind, okay, which are just deformations of the moduli or the local coordinates. Okay. So, associated with those deformations, we introduce these operators B, capital B, okay, which are just the contour integrals of the B and B bar ghosts, okay, that I introduced last time. So, basically you have to calculate the correlation function on the Riemann surface with these phi's as external states, okay, inserted with the appropriate local coordinates. You have to insert these contour integrals of the B's on the Riemann surface along those circles. Okay. But on top of that, you have to insert the product of the picture changing operators, okay, these yj's being chosen to be the coordinate at which you are calculating the tangent vector, okay, because a given point in PGMN corresponds to a given choice of this y, right, because y's are coordinates on the fiber. So, this part is fairly straightforward except for the insertions of the picture changing operators. Is this clear? Now, we have to understand how to contract omega p of phi with del del yk. Okay, these are the second kind of tangent vectors. Okay. And it turns out that there is a very simple prescription for this, okay, which is simply that you replace, if you want to contract omega p with del del yk, okay, then we pick this chi of yk factor. Clearly, there will be chi of yk factor in this, okay, it is one of the coordinates after all. You pick the chi of yk factor and replace it by minus del xi of yk. Okay, xi was the fermionic field that you got from bosonizing the beta gamma ghosts. Okay. And of course, you cannot contract with two of these del del yks because that will be 0, right, because omega p is antisymmetric. So, you can only contract with a single tangent vector of the form del del yk. Okay. So, for example, if you have omega p and if say q of these are of this kind, then you will have q insertions of capital B like this, okay, and then in the rest, okay, p minus q of them, you basically pick the corresponding y's, okay, and replace the chi of y's by minus del psi of y. Okay. And it turns out that with this simple replacement, okay, the p form omega p of phi on PGMN satisfies all the required identities. Okay. And all you need for proving these required identities is again standard techniques of conformal field theory, okay, on a Riemann surface. There are standard relations involving conformal field theory on a Riemann surface, which allows you to prove in particular that p omega p satisfies this identity that I wrote here, okay, and also that if we evaluate omega p on on shell states, okay, conventional on shell states, and integrate over a section, you get back the usual string amplitudes. Yes.
So, do you only consider the holomorphic variation of the yk?
No, not necessarily. Okay, so here of course yks are holomorphic coordinates,
Okay.
right? So at this stage it doesn't. You can also have del del. So del del yk basically means, let's say, so let's imagine that we have a section like this, okay, on which yk is varying. Okay, so this component, along this component yk is varying, right? So what this means, okay, is that you calculate del yk, okay, del t, suppose t is a parameter on this, okay, and multiply by minus del psi yk. Okay, but this variation need not be holomorphic. Okay, both y bar k and yk can vary. Okay, but the part we pick up is only the del yk del t part. Okay, del y bar k del t, okay, doesn't contract with anything.
Okay.
Okay. So this question you are asking will become relevant when you choose a section,
Yes.
right? Whether the section is holomorphic or not, and we will not demand that the section is holomorphic.
Okay. Of course.
Okay. Are there any other questions? Okay. So essentially this then specifies completely what our p form omega p is, okay, because I have told you how to contract omega p with arbitrary tangent vectors of PGMN. So now we turn to the third step, okay, construction of gluing compatible sections. Now this proceeds in the same way as in the case of bosonic string theory. Okay. We have to essentially demand that when you glue two one pair Riemann surfaces, okay, then on the glued Riemann surface, this is one pair, you have to first of all choose the local coordinate systems at the punctures to be what is induced from this gluing procedure. Okay. But now we demand one additional constraint, namely that the distribution of picture changing operators on this glued surface, okay, must be taken to be those which are induced from the locations of the picture changing operators on the original surfaces. Okay. So if the original surface had some set of picture changing operators here and here, then on the glued surface the picture changing operators should be exactly as induced from this gluing. Okay. So this is the additional condition that we put for on the gluing compatibility. Okay. Otherwise, whatever conditions we impose for the bosonic case holds. Is this clear? Okay. Now this looks quite innocuous, okay. However, as we will now discuss, it is not. Okay. There is a obstruction to doing this, okay, and which comes simply from counting. Okay. You do not need any sophisticated mathematics, we just have to count, and we will see that this does not quite work all the time. Okay. So here is the exercise in counting. Okay. So let us suppose that we have a genus G1 surface with M1 NS punctures and N1 R punctures. Okay. And we also have a genus G2 surface with M2 NS punctures and N2 R punctures. Okay. And we glue them to each other. Okay. So the total number of PCAs on the two surfaces. Okay. So this was the number of PCOs on the first surface. This is the number of PCOs on the second surface. Okay. So if you want to count the total number, okay, if you go back to this figure, you are basically counting this number plus this number, and that is what you get, okay, the number of pieces on the first one plus number of pieces on the second one. Now, suppose first that the gluing is at an ns puncture. Okay. So, if this is the case, then the glued surface, okay, we can see how many, what is the genus of the glued surface and what kind of punctures it has. So, the glued surface will have genus G1 plus G2. Okay. It will have M1 plus M2 minus 2 ns punctures. Why minus 2? Because one ns puncture from each have gone into gluing. Okay. And N1 plus N2 Raman punctures. So, how many picture changing operators do we need on such a surface? Okay, we again use the same formula, but now we apply it on the combined surface. So, 2 G1 plus G2, this is 2G minus 2, okay, plus the number of ns punctures, which is M1 plus M2 minus 2, plus half the number of Raman punctures, which is half of N1 plus N2. Okay. And you can easily verify that this number indeed matches this. Okay. So, we do have the right number of punctures. If we, so you have the right number of punctures, so that you can implement whatever we had suggested here, that the picture changing operators on the combined surface should be just the combination of the picture changing operators on the first one and the second one. But now suppose that the gluing is done at a Raman puncture. Okay. Then again we can do the counting. Now the glued surface will have genus G1 plus G2 again. Now, the total number of ns punctures is M1 plus M2 because we do not lose any ns puncture, okay. But the total number of Raman punctures will be N1 plus N2 minus 2 because one Raman puncture from each surface has gone into gluing, they are not external punctures anymore. Okay. And we can again calculate the required number of picture changing operators, okay, and this is what we get, okay, 2 G1 plus G2 minus 2, then M1 plus N2 because you have this many ns punctures, and half of the number of Raman punctures, which is this one. This, however, is not the same as this. Okay, you can easily verify that this is one more than this one, which means that when the gluing is done at a Raman puncture, okay, we need an additional picture changing operators on the glued surface. Okay, that while we can try to implement this procedure, okay, but after you have implemented this procedure, okay, we still haven't gotten all the Raman punctures that are required on the combined Raman surface. Okay, we need one more. Okay. So, now if we want to state gluing compatibility, it does not make sense to say that the distribution of puncture or distribution of PCOs on the final Raman surface is just those induced from the component ones. Okay, you have to also specify where do we insert the extra picture changing operator. Is this point clear? Okay. And it turns out that there is a prescription, okay, which is consistent with everything else. Okay. Now, it is not clear that this is the only way you can do it, okay, but this is certainly one way you can do it, and that is the following prescription. Okay. So, suppose the gluing is done in the standard manner, Z and W are the local coordinates around the Raman punctures, and we have the gluing relation ZW equal to the minus S plus I theta. Okay. So, a consistent prescription will be to insert the extra picture changing operator not at a single point, but we have to average over many such insertions. Okay. It is in the same spirit that we described yesterday, that instead of taking a given section, okay, you may be able to average over sections, okay, because after all the formal sum over sections is perfectly sensible because you are ultimately interested in integrating forms over the sections. Okay. So, the averaging that you do is this way, okay, that you take either the Z coordinate or the W coordinate, it does not matter, and insert the picture changing operators around either of these punctures with this weight factor. Okay. This operator is what I will call x0, okay, and it turns out that the x0 has some nice properties which makes everything consistent. Okay. So, this will be our prescription for gluing when we are trying to demand gluing compatibility at a Raman puncture. Okay. And I should also say that this operator has appeared before first in the work of Berkowitz and Zoibach, where they are studying the cohomology of the equivalence of cohomology in different pictures, and then also more recently in this paper, okay, where they used it for constructing a closed string field theory in the Nabu-Suar sector.
So is this is X the target space embedding, the holomorphic part of the target space embedding, or what is
this?
What is the integral?
No, this is the picture changing operator.
Ah, okay.
This is what yeah. So it's so you have to insert a picture changing operator, right? But instead of inserting at a single point, you are basically inserting an average over the circle. Okay, are there any questions? Okay. So this basically finishes the main part of the prescription for how to construct glue incompatible sections. Okay, or glue, and once you have this prescription, then we can go ahead and define the 1-pi subspaces exactly in the same way that we did for the bosonic string theory. But what I will discuss next is a technical issue, okay, which has been hidden in what I have described here, okay, and that has to do with what are called spurious poles in this picture changing operator formalism. So, the spurious poles arise from the observation that if we take the correlation function that are used for defining omega p, which means the correlation functions of the xi's and eta operators and the e to the minus phi operators, okay, then this omega p, okay, in more specifically this particular correlation function that we need to calculate to define omega p, okay, it diverges at points where no vortex operators or picture changing operators coincide. Okay, we understand that in conformal field theory, when two operators come close, there is a divergence, right, and there are physical interpretations of what the divergence means. Okay. But in this bosonized gauge system, okay, if you consider a correlation function on a Riemann surface, often what you find is that the correlation function becomes infinite, it develops poles, okay, when no operator has coincided with anything else. Okay. So, these are what are called spurious poles. Okay. They have physical significance, okay, but nevertheless you do not see directly from the conformal field theory viewpoint. So, typically the spurious poles occur at zeros of a function that involves the locations of the picture changing operators, the locations of the vortex operators, as well as the at the values of the moduli. Okay, so, it involves everything. The local coordinates themselves do not play any role, okay, they do not enter the expression for the location of the spurious poles, but otherwise it is a functional relationship, it is a complex analytic function of these variables, okay, and whenever this function vanishes, okay, you get a divergence in the correlation function. Okay, so this function I have not written down, but the explicit expression for this function is known. So, because this is a complex, it is an analytic function, okay, so vanishing of f is complex codimension 1 in this space, okay, or real codimension 2 in this space. Okay. It is a real codimension 2 subspace of PGMN, okay, or if you take a section in PGMN, it is a real codimension 2 subspace of PGMN, because you are essentially imposing two real conditions to get the 0. This divergence is in fact not special to off shell amplitudes, this arises even for on shell amplitudes. Okay. And the physical reason for this divergence, okay, this was also understood in the 80s very well. Okay. The physical reason is simply that, okay, first of all I should say where the picture changing operators come from. The picture changing operators that I introduced by hand here, okay, can be argued that they arise when we start with a supermoduli integral, okay, because after all fermionic strings should have both bosonic and supermoduli. And then if you integrate out the supermoduli, the fermionic part of the Grassmann part of the moduli space, okay, you bring down certain operators into the correlation function, and those are the picture changing operators. Okay. And what one can show is that the spurious poles appear, okay, the spurious poles appear precisely when the gauge choice for the worldsheet gravitino that you have made for carrying out integration over the supermoduli space, that breaks down. Okay, it's precisely when this condition is satisfied, you can show that the gauge choice for the world sheet gravity breaks down. So, there is a physical reason why spurious poles appear. Nevertheless, we have to find a way to get around it, okay, because a section otherwise, a typical section that you choose will intersect the spurious pole on a codimension 2 subspace, and the question would be how to integrate through the spurious pole. Because after all, you want to integrate omega over a section to define our off-shell amplitudes. So, is this point clear?
So have we already made a gauge choice for the gravitino? Is it like a delta function gauge choice?
Yes. So, the point is the locations of the picture changing operators essentially encode gauge choice for the gravitino. Exactly. So, you have chosen a delta function gauge choice for the gravitino, okay, and as you change the locations of the picture changing operators, that corresponds to choosing a different gauge, because you have taken a delta function with a different support. Yeah, so the picture changing operators arise after making a gauge choice for the gravitino. Yes.
The 1pi subsection also passes through this?
Yes, so 1pi subsection also passes through this. Okay. In fact, the 1pi subsection, one can argue in general that if the 1pi subsection didn't pass through it, okay, then the full the 1pr ones will also not pass through it, because basically you get the 1pr ones by gluing 1pi, okay, and the divergences arise, okay, when individual factors become divergent. Okay, so indeed, so 1pi does pass through it, okay, and once 1pi passes through it, then 1pr will also pass through it, because they are after all combining 1pi to get 1pi. Okay. Any other questions? Yes.
Is there a supergeometry explanation for? I mean, way to see this breakdown of the gauge choice, like is the
of the gravitino? Yeah. So basically, what you find is that the gravitino gauge slice, for a good gauge choice, the gauge slice has to intersect the orbits transversely, right? And that's precisely what breaks down at these points. That what you find is that the gauge choice, the orbits don't intersect transversely, and you see it explicitly in the form of appearance of new zero mode solutions, right? That you imagine that how do you gauge fix? You take the gauge parameter, right, and typically you get a differential equation for the gauge parameter, right, which you have to solve to find what gauge parameter you have to choose to make that gauge choice. Okay. So, for certain gauge choice, you find that a differential equation does not have a solution, because it involves inverting the Laplacian, which has a zero mode. Okay, so that is the way you see that these two are related, that the breakdown of the gauge choice is precisely when the spurious poles appear. Okay, it's the same condition, okay, that the condition that you get here is exactly the same condition under which these new zero modes appear. Okay, I mean, there is another way of seeing this more explicitly in the CFT language, okay, which is the following, that you see that the beta and gamma fields are bosonic hosts, right. So, typically if you have fermionic host fields, then they are zero modes, okay, will give 0 of the integral of the integrand, okay. Whereas if you have a bosonic host field, right, and if it has a 0 mode, then the integral will diverge. Right, and that is precisely what happens. The gamma develops a 0 mode, and the gamma path integral diverges. Okay, that is the origin of this singularity in the correlation function. Okay. So, the first guess is that perhaps by a judicious choice of section we could avoid this. Okay. But this we know is impossible, okay, for high enough genus when the supermoduli space is not holomorphically projected. Okay. It basically says there is an obstruction to choosing a global section, and that obstruction basically arises in this picture changing operator notation, okay, in the form that it is impossible to choose a section, okay, which does the job, okay, which avoids all spurious poles. Okay. So, we really have to understand how to integrate through these poles, okay, without violating. We can of course try to make an ad hoc prescription, okay, but then all these manipulations that you have been doing may break down near the singularity, right. So, an ad hoc prescription is not going to do. You have to make sure that we find a prescription that is consistent with all the identities that we have derived for omega. Okay. So, now I will try to illustrate this figure, but I think it is a little complicated. So, I will try to draw it on the board again, okay, that how we get around this problem in the picture changing operator formulation. So, in order to be able to draw anything sensible, okay, we will imagine, okay, say the moduli space is 2 dimensional, okay, so the base is 2 dimensional, okay, and the fiber is 1 dimensional. Okay, so, suppose you have a 2 dimensional base and a 1 dimensional fiber, which is this way, okay, and we will also assume that the fiber is parameterized by the location of a picture changing operator, okay, because as I said, local coordinates do not really play any role in this whole game. So, we can keep the local coordinates fixed and imagine that this is one of the picture changing operators yj, and this is our n gn, okay, of which I have drawn 2 of the directions. Okay. So, this is a 3 dimensional space, okay, and the spurious pole is a codimension 2 subspace of this 3 dimensional space. Okay. So, it is a line, it is some curve. Okay. So, let us imagine that it is some curve going like this. Okay. So, the idea is that if we try to draw a section, okay, which is a 2 dimensional surface, okay, more or less passing parallel, well, it is not parallel, but it is going along the base, okay, then it will cut it somewhere, right, that is the problem, that, and then you know how to, we do not know how to integrate through it. Okay. So, the way we are going to choose the section is as follows. Okay. So, let us imagine that we are trying to draw a 2 dimensional section. Well, my drawing is unfortunately not very good, maybe I draw it with this. Okay, so, this, imagine that this is a 2 dimensional surface. Okay. So, typically it will intersect it somewhere, okay, 2 dimensional subspace parallel to the base will intersect it somewhere, okay. But we do not go all the way, we basically cut out a circle before you reach this point. Okay. So, essentially what we do is that we integrate over the section, but outside this circle. Okay. So, you imagine that you have a line going like this and you have drawn a 2 dimensional space, but we just enclose it by a circle. Circle does not have to be small, okay, but we do not go all the way till we hit this line. Is this clear? So far we have not hit the spurious pole. Now, we erect a vertical cylinder from here. Okay, we go vertically up. No, not a fixed point. This is the locus. This line is the locus of the spurious pole. Okay, which I on the figure there I have drawn it as L. Okay, locus of the spurious pole. Okay, where this function f vanishes. Okay. So what I am saying is that we take a 2 dimensional section, but instead of going all the way through this line, you stop over a circle. So you so the shaded region is basically the region over which you are integrating. Okay, outside this circle, then you go vertically up, so integrate along this, okay, till the spurious pole has passed through the cylinder, okay, and now here you close it. No, this is a moduli space of the Riemann surface, right, on which you are integrating. Okay. In the moduli space, you come like this, you go up. Okay. So the idea is that you cannot avoid the spurious pole, right? The section has to intersect the spurious pole because it's a codimension 2 line going off, right. So, you cannot avoid it, but what you do is that you intersect it vertically. Okay, I will explain why this is important, okay, how this helps, but you intersect it vertically and then you close off the section here. Is this prescription clear? Okay, so this is what I have tried to draw here, okay, that you basically come outside the cylinder C1. Okay, you come from outside the cylinder C1 like this, okay, you just revolve this diagram, then you go vertically up till the spurious pole has exited and then you close it, this cylinder with some other part of the section. Okay. So, you would naively think that you have not really achieved anything because after all you have to integrate over this vertical part, right, and you encounter the spurious pole. Okay. But what we will now see is that it is possible to now integrate through the spurious pole without any ambiguity. Is this okay? Are there any questions? Yes.
Could you please repeat why the cylinder part is not important?
No, it is important. We are not going to do the integration over the cylinder,
Okay.
right. So, it is important, but so this is the prescription, right, and now I will explain why the cylinder part, it is important, but it can be done. Okay. So, now let us see how to integrate along the cylinder. Okay. So, you are going along the vertical segment. Okay. Now, along the vertical segment, okay, one of the tangent vectors is del del yj, right, because you are varying yj, okay, yj is going up. So, when you integrate omega on this vertical segment, okay, one of the tangent vectors is del del yj. So, you have to contract omega with del del yj, okay, and we know what it does. Okay. So, when you contract with del del yi, well here I have called it del del yi. When you contract with del del yi, the PCO at yi, which was x of yi, is replaced by minus del xi of yi. Okay. So, now we can carry out the integration over the yi variable, okay, minus del xi of yi dyi, and the yi now is to be integrated from u to v. So, u and v are basically the two endpoints here. Okay. So, this is our u and this is our v, okay, and then you will integrate over this circular direction. But now you see that this integral, okay, is just xi of u minus xi of v. Okay. Xi is a perfectly well defined object in this problem. So, xi of u minus xi of v is a well defined has a well defined correlation function. Okay. And since u and v are at the bottom and top, okay, they have no knowledge about the spurious pole, right. They do not see the spurious poles because u is big, runs over this circle over here, v runs over this circle over here. Okay. So, by doing this integral, okay, and writing it as xi of u minus xi of v, okay, we have expressed the integral in such a way that it is completely free from any divergence. Is this clear? Yes.
It's like we're taking the Cauchy prescription for the pole.
Yes, that is right.
Correct?
Exactly, yes. Yeah. So, basically because it is total derivative, right, the fact that it has a pole does not matter. Okay. If it has, so another way of saying that if you have a double pole, right, then it does not matter how you go around it, right, you always get the same answer. If only there is a single pole, that there is an ambiguity in integrating to the pole, and because it is del xi, right, xi has a single pole, but del xi has a double pole. Okay. That is why you can integrate del xi, okay, even though xi has a pole somewhere in between, okay, and you get express a difference between two endpoints which has no singularity. Is this clear? Yes. U and v are the two ends. You are integrating from the bottom to the top.
So u is the location of the PCO?
Yes. So you are integrating over the location of the PCO because you are essentially, so integrating in the vertical direction means that you are now varying the PCO location at fixed value of the moduli. Okay. Because this is the moduli direction, right? You are keeping fixed on the base and you are integrating in the vertical direction. Okay. So, for this it is important that the omega that you have defined is actually omega defined on the whole of PGN, PGMN, right, So it doesn't matter whether you are integrating horizontal direction or vertical direction, omega is always can be always be integrated. Right? Omega doesn't care about which direction you are integrating. Given any p cycle, you can integrate omega over those. Okay? And here you are integrating over the vertical direction, which basically means that you are varying the PCO location without doing anything else. Okay. So this way you can arrive at an unambiguous description, okay, of how to integrate through spurious poles. Okay. Well, unambiguous only in the sense that, of course, different choice of integration cycle will give different results. Okay. But that, as I told you, and I will discuss it next time in detail, that can be absorbed into a field definition. Okay. So this ambiguity is worse than the ambiguity that we already have, because different choice of sections will give different off-shell amplitudes. So this basically finishes our description of the construction of omega p on PGMN, okay, gluing compatible sections SGMN, okay, in which you have to do this vertical integration once in a while. And once we have said how to construct gluing compatible section, this also tells us how to construct the 1 pi subspaces, which I will denote by RGMN or PGMN. Okay, it is exactly the same procedure as in the case of bosonic string theory. Are there any questions? Okay. So now our eventual goal, of course, is to first construct the 1 pi effective action from using this, okay, and then use it to prove the desired identities, that the renormalized masses are not dependent on how you make this off-shell generalization, or it is not dependent on the choice of the section. Okay. But I will, for today, okay, in next 5 to 7 minutes, I will just give you some basic ingredients that will go into this construction. Okay, I will not write down the full 1 pi effective action today, that will be tomorrow's job, but I will give some basic ingredients. Okay. So the first ingredient is that now that we have given a prescription for constructing RGMN and also for constructing the omega, okay, we now define, so given n states A1 to n, of which maybe M are ns sector states and small n are R sector states, we define a multilinear function of the states in this way. Okay. So this you will recognize is nothing but the off-shell amplitude. Okay. All that I have done here is that I have also summed over genus. Okay. So it is not off-shell amplitude at a given genus, it is off-shell amplitude summed over all genera. Okay. So GS is the string coupling. Okay. You have to weight the genus G contribution by GS to the power 2G. Okay. Standard string perturbation theory. Of course, in any practical computation you can stop at any given order in G. Is this definition clear? Now, given this, we can also define a state in H. Okay. How to define a state in H? As I already emphasized, that you can define a state in H provided you specify its inner product with every possible state. Okay. So, we specify this quantity, this is a state in H, by simply saying that its inner product with a state of this kind, okay, where A naught is again a state in H, okay, is this. Okay, so basically this contains exactly the same information as this one. Okay, we are just using this curly bracket to build this square bracket. Okay. I should say here that this notation that I am using is all borrowed from old ideas in string field theory. Okay. Now, this object has trivial symmetry under exchanges. Okay. So, basically if gamma I is the Grassmann-ity of AI, which basically means that gamma I is 0 if AI is Grassmann even and it is 1 if AI is Grassmann odd, okay, then under the exchange of two of these, it just picks up a factor of -1 to the gamma I, gamma G. Okay. That is just a reflection of the fact that in defining RGMN, we have chosen the vertex to be symmetric. Okay. That under exchange of two punctures, the local coordinates, PCO locations, everything get exchanged. So, these are the definitions of these two curly brackets and square brackets. Is this definition clear? Now, given these definitions, one can show just by using the standard techniques of conformal field theory again, Okay. There is an important identity that it satisfies. Okay, it looks complicated, okay, but both sides of this are quite well defined, okay, because it only involves curly brackets and square brackets, okay, except for this operator G. So, this operator G is defined that when it acts on the NS sector state, it is just identity. When it acts on the Raman sector state, it gives the 0 mode of the picture changing operator. Okay. So, this appears because the way we impose the gluing compatibility condition. Okay. So, this is an identity that you can prove, okay, simply by using conformal field theory techniques. Okay. And reason that I am writing down these identities is because after we have these identities, okay, we can completely forget about where the curly brackets and square brackets came from. Okay. We can analyze 1-pi string field theory and its various properties just based on these identities. Okay. So, the first identity was the symmetry between the under the exchange of two of the AIs. The second identity is this one, okay, which looks complicated, but it is completely explicit. Are there any questions on this? So, finally, there is a third identity, okay, which I will show and then I will stop. Okay. This again just involves curly brackets and square brackets. Okay. And this gamma and gamma tilde are just the total Grassmann of all the AIs and all the A tilde i's. So, AIs and A tilde i's are again elements of each. Okay. Again, this identity can be proven by standard conformal field theory techniques on Riemann surface. Okay. Using the definition of the curly and square bracket and just manipulating conformal field theory word identities, you can arrive at this. Okay. So, next time we will build the 1-pi effective action using these curly brackets and square brackets, okay, and then we will describe various properties that the 1-pi effective action has, including gauge invariance, okay, which just follows from these three identities. Okay. You never have to go back to this definition again. Well, not never, once you will have to go back to this definition, but for most purposes, okay, we can just use these three identities that I wrote down, okay, and the definitions to derive all the results. Okay. So, I think I will stop here. Thank you.
Any other questions? Yes.
So are you saying that with this new prescription, we are able to integrate out the odd moduli and work
That's
with,
right,
the,
yes.
with the moduli space for all genus?
Yes, we are able to integrate the odd moduli, but the price you pay is that you have to add these correction terms whenever you do this vertical jump, right. That, so, you basically, so this allows you to change the section discontinuously, right. You are ending here and then you are starting from here, okay. But there is a result of this vertical integration, right, which is this, that you have to add to the full answer.
All right. Okay, well, let's thank Ashoke again for a great lecture.